There is that midterm coming up on Monday. So what we'll do tomorrow will be a review for the midterm in which maybe it would be reasonable to guide the discussion by thinking about exactly those questions on that not full points back review document. So with that out, let's carry on with what I want to talk about today, which is how to solve trigonometric equations. And I think it might make sense to start today, since there are no new ideas in this next example. Tell me, what is the solution to 3 times the tangent of 2x minus 1 plus 2 equals 1? Come down to an answer, or if you start feeling like you're getting stuck, you have people around you can talk to. Cool. How many people feel like they're coming down to a solution? Or is anyone feeling fairly stuck on how to proceed? Well, let's proceed. So, let's just investigate what this equation looks like. It looks like, well, I see this unknown x, and there's only one x appearing in this equation. So whenever you see that type of situation, you should think about, well, just think about all the things that are done to x in the order you do them, and then undo them in the opposite order. So first I see x, and I do that linear operation 2x minus 1 to it. I can think of that all as one operation because I know how to undo it. Add 1, divide by 2. Then you do tangent to it. What is the operation we have that tries to undo tangent? Inverse tangent, with this ambiguity that you're off by like a plus pi k. And what's done to tangent? You multiply it by 3 and you add 2. So let's look at that last step. multiply by 3, add 2. What undoes, well, how do you undo adding 2? Subtracting 2. So you wind up with 3 times the tangent of 2x minus 1 equals, I guess, minus 1? What undoes multiplication by 3? Division by 3. And I have the benefit that I have erasers, so I'm not going to write a new line for this. Nice. Now I see tangent of some stuff equals negative a third. What undoes tangent? Inverse tangent. So I could rewrite this as, so right now I'm here. I could rewrite that as 2x minus 1 equal to inverse tangent, or arctan if you like, of negative 1 over 3. And there are some issues here. Whenever you undo tangent, you're off by something. Because tangent is periodic, you could be in any one of the periods. What's the period of inverse tangent? Pi. So what should I add to this? Plus any multiple pi, plus pi k. Because I don't know which multiple of pi I'm off by. There's no instruction here that says what quadrant a thing should be in. Plus pi k. And I don't know, before we proceed, is there any simplification we should do? So the first thing to ask is that negative 1/3, is that a number that you know an angle whose tangent is? Do you know an angle whose tangent is negative 1/3? No, it's not on the unit circle. Right? That would be like 1 root 3 and 1 over root 3 that you could get. Or plus or minus that. But is there any simplification we could do otherwise? Yeah, inverse tangent is odd, so that's something anyway. So you end up with 2x minus 1 equal to negative arctan of 1 over 3, you can pull the negative sign out, plus pi k, where k can be any whole number it wants to be. Feeling good so far? So on the side with the x's, I now see 2x minus 1. Do you know how to get x on its own when you see 2x minus 1 on one side? Yeah, and there are no x's on the other side. There's this k that's showed up, but no x's. So what should I do to that to get x on its own? Add 1, then divide by 2. So let's do both of those in a single step. I'll get x equals negative arctan of 1/3 plus pi k. You told me to add 1 to both sides, so I'll add 1 to both sides. And then I need to divide by 2 to get rid of the multiplication by 2. Have we now gotten x on its own? So there's a solution. Let's do a bit of shtick to check that this is actually the solution. Maybe one thing we can do is, I've pulled up the graph. We see that there are multiple solutions. We can get decimal approximations by looking at the graph. There's one of them. There's another. There's another. The thing that we just wrote down, could we take various choices of k and see what that's equal to? Yeah, let's do that. So maybe I'll take k equals 0, k equals 1, k equals minus 1. We'll see what these are approximately. I'll start with k equals 0. If anyone wants to do any computations in ahead, go ahead and see what happens when you plug in k equals 1. Make sure you're in, well, what do you think, radians or degrees? You're called for radians. What sets you off that it should be radians? Yeah. And if it were degrees, like this pi would have to be a 180. Yeah, cool. So let's do it. So I'll pull up this particular calculator. Negative arctan of 1 over 3. Then I need to add 0 times pi. So I'm taking k equals 0. Add 1. divide by 2, I need to divide the whole thing by 2, so I should get another set of parentheses. That look right? Oh, well, hit enter not some other keystroke. God damn it. Alright, I'm not using that calculator then. Alright, negative 1/2. Negative inverse tangent 1/3 plus no pi's plus 1. I see the decimal approximation being about 0.339. So, let's put that down. About 0.339. Am I rounding that correctly in the last digit? Looks like. Is that one of the solutions that the graph indicates? That's encouraging. Did anyone go ahead and give me a computation when k is equal to 1 or minus 1? I was hoping someone would have. I guess it'll be easy enough to take that number and add, I guess, pi over 2 to it. Oh, people are doing it, so I'm just going to wait. We'll see what people get. So when k is equal to 1, about 1.91. Is that one of the things that I hoped to see? Excellent. And you know what? As long as we've got the calculators out, it'll be easy enough to replace that plus pi with a minus pi, I hope. Yeah, do that. Are people getting inconsistent things from that? Awesome. That's what the graph says as well. Cool. So I believe this answer. So here's the takeaway. You can see compositions of trig functions with lots of other things, and you can still solve those things. Just undo things in the opposite order the third time. If you see linear function inside of a trig function inside of a linear function, first undo the outside linear function, then undo the trig function, then undo the inside linear function. That idea make sense? Nice. So, let's carry on. So, this next one involves a different sneaky idea. So let's try to solve this trig equation. 4 times the cosine of x plus 5 is equal to 4 times the square of the sine of x. So here's something that's annoying about this. How many different trig functions does this involve? 2. So I can't just say, oh, I'll solve for sine, because then there will still be like a cosine on the other side, and there will be 2 x's floating around, and I won't be able to get one on its own. I also can't just solve for the other one that I didn't mention for the same reason. So instead, here's the game. I'll try to rewrite that so there's only one trig function in play, and then we'll be in the situation we were in yesterday, solving very similar equations. What's a relationship we could take advantage of between sine and cosine? Yeah. Yeah. So by the Pythagorean identity, we know that sine squared of anything, so x in particular, plus cosine squared of that same anything, is always equal to 1. Could you take that and solve it for sine squared? Yeah, just, I guess, subtract cosine squared to the other side. So here's the fact we get. Sine squared of x is always equal to 1 minus cosine squared of x. Sine squared of x equals 1 minus cosine squared of x. Let's think about what would happen if so that means we can replace this sine squared with 1 minus cosine squared. After we do that, how many different trig functions will appear in this formula? Just one. So we'll be able to follow the strategy we'll want. Just solve for cosine, see what cosine is equal to. I guess there's a square, so you expect like 2 solutions. That cosine could be, each of them could produce potentially infinitely many solutions. So, doing that, I see 4 cosine x plus 5 equals 4 multiplied by 1 minus cosine squared x. And now I'll pause and see how you all feel. That look like an equation that you know how to solve, at least for cosine? So, either I'll talk or I won't talk. Should I continue to talk through a solution solving that equation? Okay, seeing no hands go up, solve that equation. I'll start by solving for cosine, then solve for x. Maybe I'll make this comment that'll help you have to write less. Make up a dummy variable to have the job of cosine, so you don't have to write cosine so many times, at least in this step. It's just the review document for the midterm, so don't need it today, but tomorrow it'll be nice to have. Encourage you as you come down to a solution, whether what cosine of x is equal to or what x itself is equal to. You can compare with those around you, see how they feel. So let's come together at least for this. So what are the options that cosine of x could be? Yeah. Only one root? Cool. Does that agree? Should I talk to it? Yes. Okay, let's do it. So here's the game I'll play. I'll replace that cosine with a c, and then I'll solve for c, then I know what cosine is. So doing that, this becomes 4c plus 5 equals 4, 1 minus c squared. Right, the cosine is squared, so that becomes c squared. I want to solve this for cosine, so tell me what to do. Distribute the 4 seems useful. That will remove this c squared from the parentheses, which will be nice because there's a c on the other side. So 4c plus 5 equals 4 minus 4c squared. All right. And let's just look at what type of equation this is. What's the name for this type of equation? It's a quadratic. It looks like some of the coefficients are complicated, so I guess if there's only one you know that it really will be a perfect square, so maybe that's a hint that we could complete the square and it would just be a square already. Or we could get everything onto the same side and use the quadratic formula. And I think that's the most general strategy, so let's get everything onto the same side and use the quadratic formula. So what should I do to get everything onto the same side? Well, has anything gone wrong yet? You look like you see something wrong.
No, I don't, just because you distributed the 4 by this forwards.
Since I've distributed the 4, say again?
Yeah, since you distributed the towards the negative 4, but
Oh, well, 4 times 1 becomes 4. 4 times c squared becomes 4 times c squared.
Okay.
Cool. So let's get everything onto the same side. I guess I'll put everything onto the left-hand side, so there's a 0 on the other. Add 4c squared to both sides. 4c squared plus 4c. Subtract 4 from both sides. That plus 5 will become a minus 1 equals 0. Yeah.
When you subtract 4 from 5.
Absolutely it is. I appreciate that you phrased that very diplomatically, but obviously you're right. Yeah. So, from here the strategy is either you can recognize that this is a perfect square or you use the quadratic formula. Can you recognize that this is, well, is this a perfect square? Yeah, so you could rewrite that as 2c plus 1 squared equals 0. Oh, now it's easy to set that equal to 0. The only thing whose square is 0 is 0. 2c plus 1 equals 0 when c is equal to negative 1/2. Or, if you don't notice that, then let's use the quadratic formula. That'll give us c equals negative b, negative 4, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. I plugged things in correctly?
Where did you get 16?
Where did I get the 16 from? So there should be like, that's like the b squared term. So it's 4 squared. So let's write this all out. So I guess walk inside the square root of 4. So 16 minus 4 times 4 is 0. So there's a 0 under the square root. That's good. That's exactly the situation that, since we know the answer, we should get. So negative 4 plus or minus square root of 0 is 0, so who cares about that? Divided by 2 times 4 is 8. Negative 4 divided by 8 is negative 1/2. Cool. So there's exactly one root. It's multiplicity 2. So we need to solve cosine of x equals negative 1/2. Is that an easy equation to solve? Yeah. So let's do it. So like the starting solution will be cosine inverse of negative 1/2. But take a look at your unit circle. Is negative 1/2 a value you see for cosine on the unit circle? What angles do you see? What angle in quadrant 1 or 2 do you see that has that cosine? I hear a pi over 3. 2 pi over 3. That seems more reasonable. 2 pi over 3. Taking a look at the unit circle, people agree? Nice. I don't want to pull up my unit circle, but yeah, that sounds right. So there's one solution. What's the other solution that you see on the unit circle or by doing some trickery? Negative 2 pi over 3, or if you like 4 pi over 3, right? Depending on whether you do it by like saying cosine is even, so I don't care about, I could stick a negative sign in front. Or you could look at the unit circle and just see the other one. Which one, if you were doing this just on your own, which of those two would you probably use? Negative 2 pi over 3? 4 pi over 3. All right. Those were about the same, so I'll just write down both of the things that you could possibly get. So it looks like the solution is, well, what's the period of cosine? 2 pi. So I can stick an extra plus 2 pi k in front of all these. So x is 2 pi over 3 plus 2 pi k. Or, I'll use the negative one. Negative 2 pi over 3 plus 2 pi k. That seem pretty reasonable? Any questions right now? So let's look at the graph and see if things what things we can notice from the graph. So, we wanted to solve 4 times cosine of x plus 5 equals 4 times sine squared of x. Zoom out a little bit. So maybe I'll change the viewing window to be between 0 and 2 pi. So based on the solution that we just saw written down, how many solutions should there be between 0 and 2 pi? 2, right? 1 from each family. Do I see 2 solutions? So the other thing we noticed is we solved this quadratic and got only one solution. So that means that as far as the quadratic thinks, the graphs should like bounce off each other and not cross. Do the graphs do that at the points of solution? Yeah, it looks like. I think I'm happy with this graph. And let's see, Desmos will label the points of intersection, I think. Oh, no, they won't when it's not that. Cool. We feel all right? Nice. So let's carry on. So here's another one that uses the same sort of idea. Let's solve the equation tangent squared of x plus secant squared of x is equal to 1. So here's the philosophy that I'll endorse. So how many trig functions are there in this right now? 2. So we're in the same annoying situation, but there should be some sort of relationship between those 2 trig functions. And, well, there is. It uses some of the things that are called like the other versions of the Pythagorean formula. But I'll endorse a different strategy. Let's write everything in terms of sine and cosine and then go from there. What's tangent in terms of sine and cosine? Sine squared over cosine. So we replace everything with sines and cosines. We get sine squared x divided by cosine squared x plus what's secant? 1 over cosine. So the next bit will be 1 over cosine squared x plus 1. So, well, there are some like steps written on the piece of paper. Yeah.
Where did you get the plus 1 from?
Yeah, that's where I got it from, by replacing the equal sign with a plus, which is a mistake. In fact, if there's no equal sign, there was no equation to solve in what I wrote down, so there's nothing to solve. So, there's the equation. The options are I keep talking or I be quiet for a bit. Is there a demand that I keep talking? All right. So let's follow the steps as written. So, we still see two different trig functions, so that's a little bit annoying. But now it's sine and cosine, and we have this fundamental relationship that sine squared plus cosine squared equals 1. So we could get rid of the sine or get rid of the cosine. But maybe first let's simplify. Do you see two fractions with the same denominator? What should you do when you try to add two fractions and they have the same denominator? You add the numerators, right? Yeah. Let's do that. So sine squared plus, of x plus 1 all over cosine squared x is equal to 1. And maybe that's a good step for now. Maybe you can imagine that I'll probably cross divide sometime soon. I would like to get only one trig function, so either I get rid of the sine or I get rid of the cosine. And I guess here it suggests using only sine, but I'll see what people would rather. It'll be the same amount of work either way. Should I get rid of the sine or get rid of the cosine? Get rid of the sine? Get rid of the cosine? Let's get rid of the cosine. So, the rule that relates sine and cosine is sine squared plus cosine squared equals 1. I can solve that for cosine squared. Cosine squared x is equal to 1 minus sine squared x. So this cosine squared x I can replace with 1 minus sine squared x. So that's an important trig identity because it lets us get rid of a trig function that we wouldn't like to see in an equation, at least sometimes. So doing that, this becomes sine squared of x plus 1 over 1 minus sine squared x equals 1. People feel okay so far? Let's try to solve it. So now that there's only one trig function, I'll just imagine the trig function away. I'll invent a new variable name called s. I now need to solve s squared plus 1 over 1 minus s squared equals 1. That look like an equation that you know how to solve? Yeah, it looks like a rational equation. So your first step is get rid of the denominators. Once you get rid of the denominators, then you'll have a quadratic equation. You know how to solve those. I think lots of things will cancel also. So I'll just pause for a bit. You'll tell me what sine is. Cool. So you solve that for us. What do you get? I hear a 0. People agree? Cool. People want some more time? Should I go through the steps to get that s equals 0? Okay, let's do it. So, well, maybe I won't. Lots of people in the room did. So what's the first step that you did to get s equals 0? What's the first simplification? Yeah, clear the denominator, multiply by the thing on the bottom. So multiplying by the thing on the bottom, you will get s squared plus 1 equals 1 minus s squared. Cool. What next? I don't want to take the square root yet, because it's still like the plus 1 that's annoying. So I guess you should think like, you could think like get everything onto the same side or something. Okay, let's subtract 1 from both sides, because that'll get rid of, well, in fact, the plus 1 on both sides by subtracting 1. Then add the s squared to the other side. 2s squared equals 0. So, divide both sides by 2, you get s squared equals 0. What's the square root of 0? 0. So, s is equal to 0. Was that enough detail? Cool. So, we wind up sine of x is equal to 0. There is no second option. All right, sine of x equals 0. So let's apply some combination of inverse trigonometry and just knowing some angles. So in the unit circle, what angles do you see where sine is equal to 0? Pi over 2 is one of them. What's another one? Wait, pi over 2? Are you sure? There's the unit circle. You want sine, so that's the y value to be 0. So what two angles do those correspond to? 0 and pi. All right, so we've now found two solutions to that simple trig equation between 0 and 2 pi. So how do you get all of them now? Add 2 pi k. Do that. So it looks like the solutions are 0 plus 2 pi k. So any even multiple of pi, or x equals pi plus 2 pi k. Let's see, that'll be pi plus any even multiple of pi. So that's any odd multiple of pi. So I see x here being either an even multiple of pi or an odd multiple of pi. Well, we can simplify that a little bit, right? Yeah, how? Well, let's write them down. So if you follow this family, it's either 0 or 2 pi or 4 pi or 6 pi and so on. This family will give us pi. Pi plus 2 pi is 3 pi. 5 pi. 7 pi. Could I combine those both into a single family? Yeah, how? Yeah, just any multiple of pi. X equals any multiple of pi. How's that idea feel? Reasonably okay? Yeah, it would be, if you can recognize it as such, then simpler solutions are better. And this is certainly a simpler looking solution than that. Ah. Nice. How do folks feel about this idea? So maybe as long as we're here, let's, well, I don't know, how confident do people feel? Should we do something to double check? If you were on a test and had some extra minutes, what would you do to double check? Yeah, great. Use a calculator. Or how? Like, to do what? Cool. Let's graph it. There were two options there. You could either graph it or you could, like, plug in x equals 0 and see what happens. So let's see. So I want tangent squared of x, of x plus secant squared of x is equal to 1. So y equals 1. And I don't care about this anymore. So let's normalize the viewing window. Does it look like these solutions are just one single periodic family, all evenly spaced? Looks like. That's encouraging anyway. Let's start just listing some of them. Oh, I didn't finish. Y equals 1. All right. So we see one solution at 0 as promised. 0 is one of the solutions we wanted to see. We see the next solution at pi. I guess if you looked on your graphing calculator, you would see it at like 3.14 and some change. But you know the decimal approximation for pi to some precision. So you would be able to recognize that. Next one is at 2 pi. Previous one is at negative pi. Yeah. Do those look like they're an equity multiple of pi? Cool. I think I believe it. Groovy. So, with 10 minutes left, it's a loud dog.
I know. Wasn't expecting that.
Here's some equations to solve. The following might be a good idea. Start at the top. Start walking your way down. Tell me what Gesundheit the solutions to these equations are. So, if that's pulled up on your end, maybe I'll just remind you of these flow charts, right? You want to solve a trig equation. Start by finding some initial solutions using inverse trigonometry and symmetry, and then use periodicity to add something to get all the solutions. let's come together and just see how people are feeling on this front. So, sine of x equals 4/5. What's the solution to that? Well, what's like the first solution to that that's like the obvious one? Yeah, inverse sine of 4/5. I guess you should always be a little bit concerned if 4/5 is bigger than 1, because then there would be no solutions, but it's not. That's like 0.8. So there's one solution. You can get infinitely many by doing that. How do you get the other half of the solution? Not add pi, slightly different from that. So let's draw a picture of it. So there's the angle you just found. There's the angle you want. Adding pi would get you like that angle. So you don't want to add pi, you want to go forward by pi and then back. So not pi plus, but instead you want forward by pi and then back by the previous solution. So it'll be pi minus the other solution. So the other solution is pi minus sine inverse of 4/5 plus 2 pi k. And 4/5 isn't a number you see on the unit circle, so it doesn't simplify. If you wanted a decimal approximation, you could get one. Cool. That feel all right? Let's think about the next one. Cosine of x equals negative root 3/2. So we'll follow the same strategy. Give me one solution, then we'll add 2 pi k. Then give me another solution, and we'll add 2 pi k again. So what's one solution to cosine of x equals negative root 3/2? Yeah, cool. So, how sure are you in that? So negative pi over 6. Here's what makes me upset about that. Is like there. What quadrant is that? 4. Where cosine is positive. You need cosine to be negative, so I think you want like that angle. So, possibly by looking at your unit circle, what angle is this that gives you cosine equal to negative root 3/2? 5 pi over 6. So I see one solution at 5 pi over 6. So one solution is x equals 5 pi over 6 plus 2 pi k. And that's like half of the answers because there should be an answer right there. What angle is that second angle? Yeah, you said the right thing. Just say it louder. Perfect, yeah. The same angle, but reflected over the x-axis. Alternately, as a reminder, if your mindset right now is like the exam that's coming up, you're allowed to have a note sheet. How many people think that having a picture of the unit circle on your note sheet might be a good idea? The picture in the notes that I gave out is like really big and it's in your notes. So you probably want to make your own. You can probably make it significantly smaller and still carry all the information. So, the other one was x equals 7 pi over 6 plus 2 pi k. That's not a very good 7. Nice. So, when you see an explicit angle, an angle that you know, that gives you the right trig function, that gives you one of the solutions. When it's a number that you just know, you don't even need to write down inverse sine or inverse cosine. You can just write down that angle. But there are only like 3 numbers on our unit circle, 5 if you count 0 and 1. So it's entirely possible to not encounter those. So maybe as people are packing up, maybe I'll just see how much progress people made. 3? People are happy on 3? 4? 5? 6? Cool, I only gave you like 6 minutes to do that, so that's reasonable. So, keep this in mind for next time. Maybe think about some of these problems. They'll be not irrelevant for studying for the midterm exam. And also, think about the review for not points back, because I'll be totally willing to answer absolutely any question about this. I'll be evasive if you ask me about the review that's on campus. Groovy. Then I'll see you all tomorrow, if not during my office hour. And if you didn't grab a copy, then there's a copy.